Hello, everyone. Today we're talking about radioactive dating. Last time we talked about how we got relative ages by crater count, and we used the fact that we had absolute ages from the moon, from the lunar samples that we returned, to get absolute ages on other bodies, or at least estimates of them. So today we're going to talk about how we do that. So we do this by radioactive dating. Physicists are pretty familiar with how this works, at least in the abstract. We're going to gloss over a lot of the quantum mechanics because for us it really doesn't matter. Looking at the ages of moon rocks, the ages of Earth rocks, and the ages of meteorites. And also what we can learn from many different types of dating, beyond just the one we normally cover in first semester astronomy to talk about how old things in the solar system are. Right, so what does the age of a rock mean? What is this defined as? One of the things that this could be is the formation age, the last time this rock was molten or vapor. So for instance, most meteorites are pretty old. They've been solid rocks since the early solar system. Rocks on Earth and the moon are less old. Some of them have been melted by geologic processes or just plain cratering. The second is what's called a gas retention age, which is if the rock has some gas in it from, let's say, radioactive decay, how long will the rock hold onto the gas? And if we need that gas to estimate the rock's age using radioactive decay, knowing how long the rock will hold the gas is going to set a limit on how old the rock is. We can also measure how long a meteorite has been exposed in space, which I'm going to talk about later. This is less useful for planets, but it's useful for studying small bodies. And it's also useful if we want to study some of the Martian meteorites to know kind of their history. How long did they spend in space and how much has it changed them? And it can give us some idea of dynamics of the asteroid belt. So let's start with the basics. We use radioactivity to date rocks. Radioactivity is pretty much a random process. So if we wanted to write down equations for this, we're going to need to look at differential equations. So let's say we have a parent NP, and it's transformed by some radioactive process ND to ND, the daughter isotope. So here's our parent, here's our daughter. Parent is radioactive, let's say the daughter's stable. So the rate with time is going to be negative. We're losing parent. That's proportional to the number of parent bodies and some constant. For now, I'll just call it lambda. I'm going to set it up equal to something later. So if we integrate this, we get something like this. Integrate both of these start from NP naught at time T naught, then some future time T, we have some NP. So here we have a 1 over n integral. So that's going to be a logarithm. Here we have just a constant. And we do a little bit of manipulation. Take the, this minus this will be and NP equals, oops, I misdid my integral, T minus T naught. And P naught e to the negative lambda T minus T naught. Now notice lambda has units of 1 over time. Technically that's frequency. So let's actually just change lambda to some number 1 over Tm, T median. And so that would be the time in which the decay, the parent decays to 1/eth of the original population. It's related to an idea called half-life, but we'll talk about that later. Back to Keynote. So there's our equation. My notation's slightly different here. So the number of parent atoms at time t is the number of parent atoms at time t0 times e to the negative change in time, t minus t0, divided by that tm. And that lambda, or the 1/tm, is what we call a decay constant. Now, if you want to know if you remember, a lot of times we don't talk about that. We talk about what's called a half-life. So instead of the 1/e time, the time it takes to go from 100% to 1/e times 100%, we often talk about the half-life. How long does it take to go from 1 to 1/2? And that's just changing the base of our exponent from e to 2. So the relationship, so the Tm is directly proportional to the half-life. It's just Tm times the natural log 2, which converts our base of our logarithm, gives us the half-life. And you can reverse that if you need that constant to calculate things. So, all right, that Tm, that, decay, inverse of the decay constant, that characteristic time. Well, if we're trying to date rocks, we want to find some where we have some hope of finding parent left. If the half-life if the decay constant is really short, if the half-life's really short, what happens is it all just decays to the daughter. We don't find any of the parent. It's a probabilistic process, but eventually you hit below the threshold of where we can detect, the presence of the parent isotope, parent atom. So that means we want to pick things that have half-lives of hundreds of millions to billions of years, since we think the solar system's billions of years old. But there is a use for shorter half-lives, even if all the traces of the parent element are gone, because they can capture what was happening as the parent was decaying. All right, so let's look at these relationships a bit. So each radioactive reaction is between a parent isotope and a daughter isotope. Just like when we're looking at fusion, if you go from parent to daughter, the parent has more energy stored in it than the daughter plus the decay product, so some energy is released. In terms of binding energy, in terms of the forces that hold your atom together, that means the daughter is held together more tightly than the parents were. So for heavy elements, that means we're going towards iron, nickel, the stable elements of iron and nickel. For light elements, we're going towards iron and nickel. Now, in general, the tricky thing is that we need a kind of a process to get these things apart. While technically turning lead into iron would give off energy, there's no pathway that gets one to the other that won't take energy to start. On the other hand, turning uranium to lead, that's energetically favored. It will eventually happen on its own. There's all the steps from uranium to lead are all steps where energy goes down. Now in general, since these atoms do persist, there is an activation energy to get these things to decay. Thankfully, quantum mechanics means if you're going up against a finite energy barrier. All right, so if we have a radioactive isotope, what we're saying is the parent is holding on to more energy than the daughter plus the decay products. So let's say this is an alpha particle, and then there's some energy. But takes some energy to basically separate, to break this thing apart. Now, it is an atom. It is being held together by the strong nuclear force, while the Coulomb force will repulse, pieces of an atomic nucleus. That only operates at farther ways. So if we're looking at potential energy, now potential energy is nice because I can pick wherever my zero is. Near the atom, you're subject to the strong nuclear force. It wants to stay together. So it would take energy to try to pull it apart. But since we have a radioactive decay, breaking the atom apart goes to a lower energy. We just have this barrier in the way. Classically, you can't get through that without giving this atom some energy, without, let's say, throwing a high-speed neutron at it or something. But quantum mechanically says that eventually it will, eventually it'll go from that to this, and this is roughly equal to this. If it can get to this, if the energy fluctuations can get there, it's just a matter of time. And how high this hill is will tell you how much time you need. There's three main types of radioactive decay. We're going to ignore gamma decay. That is just the atom gives off a gamma ray because it needs to get some energy out of its nucleus to assume a more stable configuration. That's not useful because we still are working with the same isotope. Alpha decay is the atom gives off a alpha particle, which is just a high-speed helium nucleus. We didn't know what they were when we named them. That means that its atomic mass goes down by 4 atomic mass units, and its atomic number goes down by 2. We have to conserve those things. So that means that for heavy elements, for the elements that are just too heavy to hold together, even with the strong nuclear force and a lot of extra neutrons, there are 4 major decay chains because these nuclei shed alpha particles, which are mass 4. Beta decay, there's technically 2 kinds, beta minus and beta plus, but we're just working with beta minus. So beta minus decay is the nucleus emits a high-speed electron, which is also called a beta particle. The minus means that it's emitting an electron rather than a positron, a positively charged particle. And to balance out the lepton number, the number of electron-like particles, it also gives off an antineutrino. Now, that electron is negatively charged, so that means the atom has to gain, the nucleus has to gain a positive charge, so a neutron becomes a proton. So this doesn't change the mass of the atom, but it does make the atomic number go up by 1. Now, with beta minus and beta plus, which is just a positron and a neutrino, and the atomic number goes down by 1. But with those two, you can shuffle around your atomic number while keeping your atomic mass the same. That's why all these decay chains exist. They're basically the combination of alpha and beta, and this is one of them. So if you start with thorium-232, so the thorium atom, which has an atomic number of 90 and a mass number of 232, it alpha decays to radium, so it's now a mass of 228 and an element number 88. It has 2 beta decays to get it back to a thorium, but now it's 228. The number doesn't change. And it alpha decays all the way down to lead, which is element 82. So each step it's skipping 2 atoms. You can kind of see it in the picture. And that form of lead-212, is not a stable isotope and not a stable type of lead. It's still got too many neutrons. So it beta decays to bismuth, that being a bit stabler than the equivalent in thallium. And then goes either beta then alpha or alpha then beta to lead-208. And so we find 232 thorium to 208 lead, all the steps we can find traces of, though most of them you can see are much shorter than the half-life, the first jump from thorium to radon. All of them have half-lives of hours, minutes, seconds, days. I guess 228 thorium has a half-life of and 228 radon have half-lives of years, but the 232 thorium has a half-life of 14 billion years. So that's the slow decay. Once it stops being that isotope, that element and isotope, it's on its way to lead. So anything that has a atomic number that's too heavy, it needs to decay by alpha particles. It's heavier than lead. It has an atomic mass that is divisible by 4, will follow this decay chain. It's called the 4n decay chain. And there's a 4n plus 1, 4n plus 2, 4n plus 3. 4n plus 1 is kind of boring. The other 3 are similar. Take heavy stuff like thorium and uranium, which are radioactive but have really long half-lives, and take it down to lead, the last stable isotope. All right, so that's what radioactive decay is. Let's look a little bit at the math. So we already went into how you get the number of parents. After some future time t, if we can estimate that from them. That's not particularly useful because we need to know how much parent the rock started with. Well, we can say, okay, some of the daughter product was made by the parent. So what we have is all of the parent becomes a daughter product. Now, a few processes, especially if we go back a slide, notice the 212 bismuth at the bottom. That can either become 212 polonium or 208 thallium. And so what tends to happen is there's what's called a branching ratio. Some of it, probabilistically thinking, will alpha decay to thallium, some of it will beta decay to polonium. And that's represented by that Greek letter psi. So psi is the branching ratio, xi. It's basically what's the probability of this particular daughter from the reaction. Now, if only one's possible, then psi is 1. So that sum, the number, anything that hasn't decayed, so we know how much the parent is. Anything, we know how much we started with the parent, let's assume. We know how much we have now. The difference is going to be daughter ratio, again, mediated by that constant, by the branching ratio. But we also have to consider how much of the daughter we started with. And that's annoying because we don't know how much parent we started with. If we didn't start with any daughter, then we could assume that the number of the parent plus the number of the daughter is constant. That we're not adding anything to this rock. But if we don't know how much the daughter started with, then we know that the total parent and daughter is constant, but that's not particularly helpful because we don't know what they originally look like. We know that there's more daughter now, but we don't know how much it started with. So one solution, this is the simple solution, is you pick something where there is absolutely no way the daughter product exists. Now, the best example of you doing this is potassium-argon dating. So potassium-argon dating, potassium-40 decays into either argon-40 or calcium-40 through a beta minus or beta plus. Argon, calcium-40 is going to take up a mineral form. It's going to be in whatever mineralogical structure that the potassium-40 was in. But argon-40 is a noble gas. It would not be in the original rock. It would have escaped from the melt, from the liquid rock. So when the rock just solidified, it would have had no argon-40. Now, that means any argon-40 had to have come from potassium-40. And we can estimate how much, and since we know how likely the potassium decay process is to create argon-40 rather than calcium-40, we'll know how much potassium-40 we started with, and you calculate the age that way. There's just one problem. we have to assume the rock traps all the argon-40, and that's not necessarily true. There's that gas retention age thing I told you about, that we'll find a minimum age for the rock, but the rock could be older if some of the argon got out. And sometimes that's useful. Sometimes, you know, knowing this rock is at least so many billion years old is pretty handy. So we'll go through how to solve that problem in a class. Now, a more robust solution is don't just measure how much parent and how much daughter there is, but you add a third one, a reference isotope. So we have number of parent nuclei, number of daughter nuclei, and number of reference. That's a little tricky. You know, we're stuck with the how much of this rock did the rock start with. But what we can do is make the assumption all parts of this rock are the same age. So even if they start with a different mix of elements and different minerals in this rock, they all solidified at the same time. Now we need one more bit of information, which is that our reference isotope has to be the same element as the daughter isotope. So the reference isotope is stable, it's not produced by radioactive decay, and it is the same element as the daughter isotope, so they act pretty much chemically identical. What we can do, and I'm going to go back to the whiteboard. So let's assume our branching ratio is 1. Let's say we don't want to deal with that. So we have number of daughter equals number of daughter at time 0 plus the number of daughter isotopes produced by the parent. So that'll be number of parent at time 0 minus number of parent now. And we had that expression for the number of parent isotope. So we could, you know, figure out what this is in terms of this. Now what we're going to do is, instead of looking at the number of atoms, we're going to measure this as a percentage. Number of daughter over number of reference atoms. So now I can break up this sum. And what I'm going to do is multiply both sides of this by number of parent at now. So we have number of parent naught minus number of parent divided by number of parent now times, there we go, number of parent divided by number of reference. So I multiplied both sides by the same, or both top and bottom by the same thing. This number is essentially 1. And then just rearranged it. Now, why is this important? This number, because number of parent only depends on our starting, you know, number of parent isotopes only depends on the original amount and time. This number is essentially only depends on the age of our rock. We can even divide out number of parent equals number, there we go. Number of parent equals number of parent not e to the negative, I'm just going to call that delta t over tm. So we could divide out n number of parent not and get an expression that only depends on time. So this bit only depends on time. So now if we can measure these two things. This is the number of daughter nuclei versus the number of reference nuclei, number of parent nuclei and reference nuclei. These are the ones that exist at now. We still don't know this. We don't know how much daughter nuclei we started with. So what we're going to do, if our daughter and our reference nuclei are the same isotope, then our assumption is we're going to assume that when the rock was melted, chemically those two isotopes are the same. So we're going to assume that the ratio is the same throughout the rock. When it was melted, we can mix it up. So that would mean that the NDO over NR is a constant throughout the rock. And NPO minus NP divided by MP is also constant throughout the rock because it only depends on the age. It can be a different number if the rock, as it'll change as the rock ages, but it should be constant throughout the rock. So that means we have two constants that are only determined by the actual rock and two ratios of things we can measure. So what we can do is fit a line. Is we measure NP over NR and ND over NR, in many spots in the rock. And if the rock is all one age and started well mixed, so that daughter isotope and reference isotope were the same throughout the rock, then all the data should fall in a line. And the slope of the line should tell us the age of the rock. This is called an isochron, same time. So this is kind of a simulation, a model of what's happening. So here, instead of NR, this is called DI to remind us that it's the same element as the daughter, but a different isotope. And to be clear, it has to be something that's not made by radioactivity, otherwise that messes it up. It has to be something where we expect that it's not going to change, the number of atoms of it is not going to change as the rock ages. So we're going to start with molten rock. And we have the radioactive decay, so we go from less parent and more daughter. And then when the rock solidifies, it has different parts. It has different, when the rock solidifies, the parent and the daughter are chemically different. So different minerals in the rock will have different ratios of parent to daughter, or parent to reference isotopes, since the daughter and the reference are chemically the same. But as they decay, they all do it at the same rate. You continue to get the line, and the y-intercept is just how much daughter isotope we started with, which is not going to change. So, and this just traces what happens. The more parent you start with, the more of the daughter isotope you're going to end up with relative to the reference isotope. So here's an example of one from a paper. This is looking at rubidium-strontium dating. So here, rubidium is the parent, strontium 87 is the daughter, and strontium 86 is the reference. And you can see what they did was to find the age of this impact structure was they measured a bunch of samples of rocks that would have melted during the impact, and then fit a line to it. And then they calculated the parameters from that line to get both an age, which in this case is 1.8 billion years old, and the initial strontium ratio. So originally the ratio of strontium 87 to 86 was 0.7. And you can see this is a pretty slow decay. So there's still a lot, it still ranges from just 0.7 to 0.76. So, it hasn't changed much. Most of the rubidium is still rubidium rather than strontium 87, but we can use this to fit an age. And it does nicely minimize some of the processes, because if you don't get a line, that tells you something went funny. One of your assumptions did. So on Earth, when we do this, we find zircon crystals that are 4.4 billion years old, but few rocks, or rather the rocks have gone through sedimentary and metamorphic processes so that they're made of different stuff that solidified at different full time, but we can still take the different samples in the crystals to do it. Zircon uses the uranium to lead decay process. So uranium happens to form as an impurity in these crystals. Now, this process is actually something called lead-lead dating, which is two isotopes of uranium decay to two different isotopes of lead. Uranium-238 decays to lead-206. Uranium-235 decays to lead-207. So 38 is the 4n+2 decay chain, and 35 is the 4n+3 decay chain. And each reaction has a different half-life, so it acts as a nice check. And since uranium and lead, uranium-238 and 235 should be chemically identical. They should do the same kind of chemistry, as should lead-206 and lead-207, gives us a nice extra security. In addition, there is lead isotopes that are not radiogenic, not produced by radioactive isotopes. Now, for the moon rocks, we talked about how they work as a crater aging, and our crater method. And this is, again, more charts of the time in terms of billions of years old. And again, that's plotted versus craters. So you can see both the a linear scale and a log scale, depending on which way you want to look at, depending on whether you want young ages or old ages. Now, the oldest rocks in the solar, so the moon rocks, they are actually slightly, some of the oldest moon rocks are slightly older than the oldest Earth rocks. But the oldest rocks we have are meteorites, in particular a class called chondritic meteorites. These rocks pretty much formed at the beginning of the solar system and have not changed since then. They've never been melted or vaporized. The Allende meteorite in particular has chondrules, which are little round kind of bead-like structures, which have an age of 4.566 billion years old, or 4,500 million years old. And you can see this is, again, a lead-lead dating system. We're looking at both the uranium, two different uranium to lead decay chains. Now, one of the interesting things that we can do is try to even break those meteorites down and look at the different parts to get us a history of the early solar system, see if we can resolve when did different structures in these meteorites form. Now, one of the really interesting things is in these meteorites, which again, they've basically sat in space for 4.5 billion years, we find what are called pre-solar grains. These grains in particular have really weird isotope mixtures. For instance, a grain might have most of its calcium be calcium-44, while on Earth and on the moon and other places in the solar system, it's mostly calcium-40. This might suggest that these grains came from other stars, that they never melted when we formed the solar system. They were just incorporated into these into these objects that then became meteorites. So that's kind of cool. Let's talk a little bit about what we call extinct nuclide dating. So how we can use short-lived radioisotopes to make timelines, even though all of the parent has become daughter products. So 26 aluminum, it was unusually common in the solar system. It's a radioactive element. It has a half-life of about 730,000 years. So, it's long gone. Nowadays we make, it's an artificial isotope. Decays to 26 magnesium, which is one of the beta decay. All of it is gone from the solar system, but we still can use it to offer relative ages. Now, how we do this is we can figure out how much aluminum and how much magnesium a rock has because we pick out what are non-radiogenic isotopes of aluminum and magnesium. So those are isotopes that are both stable and they're not made by any radioactive decay we know about. So the aluminum should act all the same. Doesn't matter if it's radioactive or not, or how many neutrons it has, it's all going to chemically act like your aluminum. Only depends on what the electrons are doing, and the electrons don't care. So, and the magnesium should all act the same. So let's say grain A forms first. There's still some aluminum-26 around. And it's mixed in with the stable aluminum-27 and all the different magnesium isotopes. Now, what's going to happen is it's going to be enriched in magnesium-26 because it started with some aluminum-26 and 27. So we could estimate, and the more aluminum it started with, the more aluminum-26 it would have started with, so the more extra magnesium-26 it had. And This would tell us something of the age of the meteorite relative to when the aluminum-26 was introduced to the solar system. How long has it been solid before all the aluminum decayed? And in particular, the important thing is that the parts of the meteorite that are aluminum rich will have more magnesium-26 than the parts of the meteorite that aren't. Now, why is this important? Well, because this is going to tell us something about when the cores of planets form. So let's pick another radioactive decay. So we have hafnium to tungsten, hafnium-182 to tungsten-182. Now, hafnium is what's called a lithophile element. That means it chemically likes to hang around with silicon and oxygen and aluminum and magnesium and the elements that make up rocks. Tungsten is what's called a siderophile element. That means chemically it likes to hang around with iron and nickel, the stuff that would sink down to the Earth's core. So the hafnium is going to decay to tungsten, which has a symbol of W. Now, if body A forms its core early, it's going to carry most of its tungsten down into the core. But it's going to leave behind the hafnium-182. And that hafnium-182 is going to radioactive decay into tungsten. And if the body is solidified and no longer forming its core, the tungsten is going to stay in the upper layer, stay in the crust and mantle. So it's going to be enriched in tungsten-182 compared to other isotopes of tungsten. Now, if we form the core later, most of the hafnium-182 was decayed, it's going to just act like the rest of the tungsten and just go to the core. So the tungsten will be less enriched in tungsten-182. So here's kind of a study that looks at this hafnium tungsten dating and says, okay, let's call the time the Earth and the moon formed 1. Let's say that is our 0. Let's look at metallic meteorites. Metallic meteorites, we think, came from metallic meteorites, and by extension, metallic asteroids, we think, came from larger parent bodies that had formed cores and then were broken apart. So you end up with metal-rich asteroids and rock-rich asteroids. And using this hafnium tungsten dating, we get that those bodies formed their core or finished forming their core before the Earth and the Moon finished, which might mean they were smaller and formed quicker. All right, so one more thing is I mentioned we could figure out the age of things in space, of how long something spends in space. And that's what we're going to talk about, which is if you have a meteorite and it's in space or it's sitting on the surface of a parent body that doesn't have a magnetic field, it's exposed to cosmic rays, high energy particles from all over the sun, the Milky Way, extragalactic sources, all kinds of stuff. And the cosmic rays, when they hit atoms, sometimes they can, they give them enough energy to reverse a radioactive process. They become a radioactive isotope. This is, for instance, where Earth gets its carbon-14. Now, cosmic rays are blocked by rock, even at just a meter of rock. So what we can do is measure how long a meteorite has been sitting on the surface of an asteroid or in space by just measuring when were we creating short-lived radioisotopes. So for instance, this is looking at Martian meteorites. We want to try to figure out when they were launched in space. So each of these symbols is a different chemically different. But if a rock has a similar chemistry and a rock has a similar exposure age, that might how long it's spent in space, that might indicate, or on the surface of a body, that might indicate it came from the same event. So that all the ones that are marked with stars or upright triangles or circles, or most of the ones that are marked with squares, might be from the same impact event that launched lots of rocks or launched some big rocks that were broken into smaller rocks. So that might be useful information. You can also see typical ages, tens of millions of years. Generally speaking, stuff in the inner solar system can only hang around for tens of millions of years before it hits something. So meteorites are kind of are going to be our calendar. They're the oldest rocks we have, and by convention, one certain type of grain, something called calcium aluminum inclusions, are considered our time zero for solar system formation. And we know that age to within 1 million years. And one of the interesting things is we can explain why a lot of the different isotopes ratios in the rocks of different objects by things like radioactivity, some of those short-lived radioisotopes, or other processes based on mass, as we talked about earlier, so that it tells us that the solar system started pretty well mixed. What we talked about today, we talked about dating. How do we know how old things are? And this is important because we're looking at meteorites. And those are often unchanged from even before the Earth and the Moon, or at least the oldest rocks we have from them. And this is going to help us figure out how the solar system formed, which we're going to talk about later. Next time, though, we do need to spend more time talking about small objects in the solar system before we talk about solar system formation. And I'll throw in some of the meteorite stuff I skipped from in there.